What is the most you can get from a DIY vacuum former? Answering that question requires a vacuum former. This one's called former number 51. Here's a picture of number 15. This one was number 30-something. Many years ago, designing and building vacuum formers was my summer job. About 50 of these shipped out of this garage to places all over the world. They worked pretty well, but they did have some limitations. So for this new build, we are going to figure out exactly what those limitations are. The question I aim to answer is how good can a mid-range DIY vacuum former really be? Even if you don't build a machine like the one in this video, I will cover all sorts of general concepts that might be helpful in your own build. We'll also troubleshoot common problems along the way. Let's talk about price. This machine can be built for about $300. A commercial vacuum former with a similar build platform will run you between $1,000 and $2,000. These machines cost as much as they do mainly because of their vacuum systems. They create a much higher vacuum and can achieve greater detail in their plastic shapes than we can with today's build. As tested with a new shop-vac and a few other items, this build was closer to $450. There are several vacuum options. An internal mount is a fine choice. These motors can be purchased for about $100. They are extremely noisy. I thought I might be able to use my dust collector to create the vacuum for this machine. Its overall wind velocity seemed to indicate that it would perform well, but it did not in the end. The next thing we need is a way to heat the plastic. Again, there are many good methods to get things up to temperature, but today we are using a replacement heat element for an electric grill. I like these mainly because they are available in a range of sizes, they put out a ton of heat, and there is no need to wire anything in some cases. Large oven-size elements for building big vacuum formers are also a possibility. My old vacuum formers had a plastic tray that flipped from one side to the other. When configured like this, the hot plastic would droop to one side of the platen during the flip. This creates undesirable thickness variations in the formed plastic that can sometimes lead to warping of the finished parts. So for this new build, the heater is going on top to eliminate this issue. The metal hood is a specific aluminum baking pan. It's mainly chosen for its dimensions as they relate to the heat element. However, its nearly flat sides and top edge make it easy to machine. Ideally, the heat element would be larger and fill the extents of the pan, but finding the perfect combination can be difficult. The supports for the heater assembly will create rigid guides to make sure the plastic tray can be slid down onto the platen as quickly and as accurately as possible. The platen or build surface is where the heated plastic is formed. It's made from a perforated aluminum sheet on some pegboard that sits atop a few half-inch plywood boxes. In order to maximize the build volume of this machine, we need a tight fit between the plastic tray and the platen. When the hot plastic stretches over the edge, it creates a seal that allows the vacuum to be pulled. Other than the heater components, all of the parts of this vacuum former were purchased at my local hardware store. Next up is the build portion of the video. I made an effort to keep it under 10 minutes long. If you want to skip it and jump right into testing, that part begins at around the 12-minute mark. The top of the platen is made from pegboard with 1-inch hole spacing. I make an effort to trim it so that after glue up I have holes all the way to the edges of the platen. After building my desk, there is a lot of half-inch Baltic birch laying around, so that's what I'll be using today. Any half-inch plywood or MDF should also work well for this process. I would suggest having a table saw, router table, and drill press for this particular build, but you may be able to modify the design to accommodate for your tool selection. Keep in mind that accuracy in this build will determine how well the device functions. My dust collector port attaches here. A shop vacuum will not need this big a hole. To help improve accuracy, each hole is pre-drilled before the box is glued together. I cut out the top of the main vacuum box. One large hole is the most efficient way to get air from the build surface into the vacuum. Drilling multiple smaller holes is an option, however this will create an obstruction to the airflow. We need to keep in mind that during the vacuum forming process, the hot plastic drops below forming temperatures within a few seconds. These moments are critical for achieving the best forming results. That's why even minor performance tweaks can be beneficial in the long run. Here's another opportunity for a small improvement. This box could be closed off with a flat bottom, but when we cut the internal volume down by half using a divider, we also reduce the workload on the vacuum. The smaller the cavity is, the faster the vacuum will be able to evacuate air from the chamber. Now we make the metal parts using some 3/4 inch aluminum channel and 1/2 inch square steel tubing. You can find the shopping list as well as drawings for these and everything else in the description. The aluminum forms 2 frames that will hold the plastic sheet for forming. One has a handle and one does not. When it comes to this type of stock material, I always like to make these parts slightly too long. This is to compensate for deviations in the cut angle. Then on the disc sander, I square up the end and grind the part down to the correct length. I make these holes a bit oversized to account for variations in the brackets and hole placement. These things are inexpensive, but only 90 degrees some of the time. Before assembly, I stretch them open or closed until they are completely square. A vise will help keep the frame from twisting during assembly. This particular frame gets the handle, which receives a few extra bolts and nylon spacers. The spacers are oversized so their position can be adjusted as needed. We want to run these as close to the uprights as possible without preventing the frame from sliding. The uprights are 1/2 inch square steel tubes. If you are trying to make one of these without a drill press, I would suggest using aluminum angle instead. To help reduce drill bit wear and tear while drilling into steel, I like to throw a little lubricant onto the workpiece. In this case, I'm using some tapping fluid. All the uprights are identical except for one that has holes for cable routing. With the frame locked in, I can now position the platen. There's not a big gap in between these parts, so I need to make sure that the platen is well inside of the frame's maximum range of movement. Then I mark its location, figure out the center point of the corner holes, and transfer that position to the vacuum box like so. Rounding the edges of the platen improves the quality of the vacuum seal and makes it easier to remove the plastic after forming. I mount this surface using deck screws. Countersinking the holes is a must. The top surface must be flat for the next step. Now we add a sheet of perforated aluminum to ensure that vacuum pressure is not blocked during the forming process. If the hot plastic manages to plug the small number of holes in the pegboard, vacuum pressure will be cut off and the part will not finish forming. A second piece of perforated metal will function as a heat spreader. I prefer a thicker piece of metal for this task, but having this stuff sheared is expensive. Aluminum sheeting is often stocked at your local home improvement center. Look for a sheet that is not heavily damaged. The flatter it is, the better. If you can find these without paint, that is preferred. Cutting down a row of holes with a tin snips will make this go smoothly. For the easiest cutting of all, a metal shear is definitely the way to go. The cover gets tacked in with a few small nails. Any holes in the box get sealed. This vacuum port can be sealed as well. Rubber feet and some handles are a good option. Now let's wrap this handle. We need a few extra holes for the bolt and nut so that the surface of the handle is completely flat. I'd like to use felt pads to create a cushion for the plastic tray. The heat unit is the last major component to go. Some holes are required. First, I'll mount the heat spreader. When cutting this to size earlier, I checked to make sure that the large perforations aligned with the flat edges of the baking pan. Now I mark those holes at regular intervals, 3 or 4 per side, and then drill them out. There is enough space to use a 4x40 nut and bolt to secure this piece, but tapping the holes is also a fine choice. Next up is drilling a hole large enough to pass the power cord through. Deburring is definitely required. There are 2 mounting tabs on the coils. I want to slide the element into place, mark the holes, and drill those out. Only the top of the tab should drop through. Last step is to add some holes for the support structure. These are a bit oversized for adjustments if required. Now for final assembly. Two sets of nuts, bolts, and washers hold the element in place along with 2 retention rings that secure the coils. The hood is then lifted into place, screwed in, and the fit on the plastic tray is tested before tightening everything down. Then with a few 4-inch eye bolts, I route the cable away from the heat source. This configuration also helps prevent power cord contact with the moving plastic tray. Last thing to do is add the heat spreader. That's it for now. Let's find out how this thing works. First of all, what does the heat spreader do? Not only does it reduce the overly high temperatures of the bare element, but it also promotes a smoother temperature gradient. These are both good things for even heating of the plastic sheet. The left and right sides of the hood are a bit too cool. This is a direct result of the heat element being slightly too small. This vacuum former was designed to accept a 12 by 16 inch sheet of plastic. The size was chosen specifically because it divides into a 48 by 96 sheet of stock material with no leftover scraps. Binder clips are used to secure the plastic. My method of holding up the plastic tray is a bit of an afterthought. I thought that I could use some magnets, but that didn't come together as planned. I also wanted to avoid 3D printed parts because they might warp from the heat. This method functions but leaves something to be desired. To test this machine out, we will use this block of wood. In this case, we could call it a mold, tool, or buck. These are all common vacuum forming terms. We're using this block because it's actually a challenging shape to form. It's somewhat large, it has flat sides, surface detail, and sharp corners. All of these things can be difficult to vacuum form successfully. Keep in mind that you may want to run your vacuum and heater on different circuits. They both pull a lot of power and can cause a breaker to flip in the middle of forming. Time for the first run. Not great. Maybe it's a fluke. Let's try that again. Still not good. You can try to push the plastic down on the sides, but I think this is generally an ineffective way of dealing with this issue. How about PETG? Also, a lousy performance. It appears that we need further modification. My best guess is that we are low on both heat and vacuum pressure. The extents of the platen surface get even airflow. That's good, we want that. I stuck a vacuum gauge onto the unit and found the real problem. We're getting 0 vacuum. Same thing with the gauge in the upright configuration. Clearly, the dust collector is great at moving air, but provides little suction. One trip to the hardware store later, and let's try out the biggest shop-vac I could buy. Still nothing, not even a single pixel of movement on the gauge. The turbine vacuum motor produces way more torque and suction than the impeller fan blade on my dust collector, but neither achieves high vacuum. For that, you will need a vacuum pump and a vacuum chamber or tank. This is not one of today's upgrades. If this sort of system was added, the cost of the build would creep into the range of a comparable commercial unit. And at that rate, you may want to just buy one rather than building one. Let's do a different test. With the dust collector running, this is how much pull force we can achieve before the vacuum is overcome. Running the same test with the shop-vac produces noticeably higher suction. This will be the best option for us. Lastly, I added some insulation to the hood to help reduce heat loss. These two blocks at the sides help take up extra plastic and reduce webbing at the corners of the block. This is a highly recommended technique for tall objects as well as anything with sharp corners. How do these things affect performance? Dramatically. Overall, the level of detail is great, and the bottom edges are crisp. This is about as good as it gets for a large block of wood. Let's try something much thinner. Also good. When forming parts like this, it is important to keep the plastic more cool. If it heats up too much, the sag in the plastic sheet will fold over itself the moment it hits the platen. Here's a look at the reverse side of the part. You can see how the detail in the corners varies based on how open or closed the shapes are. The tighter the space is, the less detail we are able to pull. When designing a tool, keep this concept in mind. You may have noticed some smoke in a few shots earlier. This is a problem. The added heat from insulating the hood is causing the polystyrene to reach its smoke point. Keep in mind that you should only ever use a vacuum former with plenty of ventilation, and in some cases like this one, you should wear a respirator. I put my machine on a rolling cart so that it can be as close as possible to a source of fresh air. In trying to bring the heat down a bit, I cut a vent hole into the insulation that is the size of the heat element. One of the reasons why I prefer clear PETG over HIPS is that it doesn't smell bad and it doesn't smoke. It is, however, 2 to 3 times more expensive than HIPS. So for testing, styrene is an ideal material. Without insulation on the hood, it takes a full 8 minutes to warm the plastic, and it never quite gets to forming temperature, which is 160 to 205 C. With half insulation, the plastic temperatures are mostly within forming range, but the center of the sheet is too hot. With full insulation, it's ready to form in only a minute and a half. The temperatures, though, are way too high for HIPS. I decided to use a fan controller to cut the power back on the heat element. This is not the right tool for the task. The excess electricity is burned off by a resistor inside of the device, and at these temperatures, it may not last very long, or at worst, it could potentially catch fire. With that in mind, let's try a few different settings. Something worth noting is that it takes about 15 minutes to get the heater up to temperature. With heat set to medium, the time until forming temperature is quite long. Unfortunately, I updated the app for this camera, and all but 2 of the temperature readings disappeared in the process. Regardless, it is noticeable that this is not quite warm enough. The lower edge of the plastic is much too rounded. Now at medium-high temperature, we are ready to form in about 5 minutes. Although the thermals seem to indicate that the temperatures are too high, there is little to no smoke. Details are definitely better than medium heat, but I would not call the lower corners crisp. Now for medium-high. Much faster heating, but now we've got smoke. Unfortunately, this is the best detail yet. Here's what PETG looks like on medium heat. Terrible. Now let's try medium-high. Much better. So as you can see, DIY vacuum formers can be quite capable, but their limitation in the end is their lack of high vacuum pressure. We can crank up the heat to compensate for this, but in the end we push the plastic beyond its acceptable limits. The plastic I used for these tests was 0.06 inches thick. More highly detailed parts can be produced with 0.04 sheets. Part of the reason for designing this machine with the heater on top with solid guide rails is to allow the heated plastic to be applied to the mold in as little time as possible. Thin plastic cools more rapidly and drops out of forming temperature even more quickly than the thick stuff. If you are trying to form with plastic much thinner than 0.04, the pull, as it's called, might fail due to rapid cooling. For the project I'm working on, my preference is the 0.6 thickness. This is because it produces robust parts and can form tall objects without the plastic stretching too thin and becoming flimsy in the process. Here's what the thermals look like from the other side. Some compressed air or a leaf blower will cool down the plastic quickly. This is important when using a 3D printed mold. I have already designed a complex mold for some prototype packaging, but this is outside of the scope for this already 20-minute long video. A quick note on cutting vacuum-formed plastic. I wouldn't describe it as fun. You can cut this stuff on a bandsaw, but it makes a truly horrible noise and puts static electrified dust all over the place. I prefer a utility knife, but the flat sides cut easily and the corners are thicker and can be quite hard. This creates a situation where the knife can accelerate suddenly, so wear cut-proof gloves and don't cut towards your body. That about wraps this video up. Soon I will go live with a 6-part series all about how this desktop product was made down to the absolute finest detail. If you haven't noticed, I enjoy the details. One of those videos will be all about vacuum forming prototype packaging. If that sounds good to you, be sure to like and subscribe to be notified when those videos drop. The most requested video on my channel is how to make an animation. That video, or possibly a series of videos, is coming out next. Let me know if you all want to see anything specific about the process in the comments below. Many thanks to my first and currently only patron, Jaga G. You are truly a handy fan. Sorry about pronunciation. Probably. Everyone else, feel free to donate with PayPal or become a patron on Patreon to make sure there is lots more content like this in the future. And as always, thanks for watching.